So, hello everyone, we are going to start the third lecture of week 5, that is transient growth kinetics. So, let us quickly revisit what we discussed in the last lecture. We discussed microbial growth kinetics, particularly if you remember there are interaction between environment and the biological phase. And then further we assumed there should be certain biological and environmental phase assumptions, and in fact at the end there can be structured, unstructured, segregated and unsegregated models, and there can be combination of these 4 parameters. So, one can be unstructured and unsegregated, this is the most ideal one, and structured and segregated, that is the actual case. Then further we discuss the monad equation, and based on this we solved a couple of examples. So, in today's lecture we are going to see transient growth, because monad equation applies for the steady state conditions, steady state in the continuous culture or during the exponential phase of the batch culture. But for the transient growth, what is transient growth and how we can model the transient growth. So, we will be seeing next unstructured batch growth models, and further we will see the growth of filamentous organisms. So, we can quickly see what we discuss the monad growth kinetics. It says mu is a function of both x and s, and mu equals mu max s upon ks plus s. Mu max is the maximum specific growth rate and ks is half saturation constant. In fact, you can see this is ks, this is mu max. The similar to this monad model, in fact, in the last lecture we also discussed while deriving the monad that Tessier model. It says mu equals mu max 1 minus e to the power minus s upon ks, and you can also see this Moser equation. It is kind of a Hill model. It is a s to the power n and s to the power n. It is kind of a Hill model. So, these two are algebraic solution. Algebraic equation, and they render algebraic solution for the growth equations. While in the third one, this quantized model, it says this apparent ks, and apparent ks, or you can say ks apparent equals ks into x. So, it says this specific growth rate is also dependent on the biomass concentration, or you can say it says mu is proportional to x minus 1. So, these are few variations of monad equations. Now, we are going to what is transient growth. It is a non-steady state growth phase of microbial growth. During this transient growth, one option is cell adaptation to changing the environmental condition. It may be the temperature, pH, or even the substrate. It helps in understanding and optimizing the microbial growth in different mode of operation. You can change the mode, that is even giving the environmental stress to the microbes. and ultimately change in the environmental or cellular conditions. What is the importance of transient kinetics in bioprocessing? This is observed when system is in a perturbed state. There is a no steady state, some changes has taken place. For example, intermediate substrate addition, shift in the oxygen supply or the temperature change. And whenever you are observing this transient perturbation, it gives the indication for the process control that some changes are there and necessary correction need to be made, and necessary corrections need to be made for the process control, scale up and optimization. So, one example you can see transient growth, diauxic growth. Here you are seeing the time and number of cells. There are two substrates, glucose and lactose. So, you can see there is a two growth phase, one is up to here, this is the first growth phase and there is a second growth phase. And there are two lag phases as well. There are two lag phases as well. So, what it says, the first glucose is being utilized as a preferred nutrient, and once glucose is over, now it is adapting to the new environment, a new substrate condition, it is again showing the lag time, then it is utilizing lactose and reaching to the growth phase. So, E. coli grows in the medium containing two carbon source, glucose and lactose, leads to consumption of glucose first followed by lactose utilization. So, in the first lag phase, cell adaptation to the media, first exponential phase, rapid growth of cell utilizing the glucose. Now, the second lag phase, glucose is exhausted and cells are now adapting to the lactose metabolism. Second exponential phase, that utilization of lactose. Further, there can be stationary phase, the substrate depletion stops the microbial growth. So, in this way we are going to see exponential phase and there is a stationary phase here. Now, further we can see what is the unstructured batch growth model. So, we are going to see few simplest approach to model the batch culture. As we know, we are having different phases, lag phase, growth phase, stationary phase and death phase. So, we will be discussing these three laws, Malthus law, logistic equation and Monod equation. This we have already discussed, that how different phases, lag phase, growth phase, stationary phase and death phase can be explained in terms of mu and mu max. So, in case of growth phase, mu equals to mu max. In case of stationary phase, mu is 0, and in the case of death phase, mu is negative, mu less than 0. So, Malthus law, what it says, once there is a growth, dx upon dt, this is the rate of biomass growth, is a function of mu specific growth and fx, x as well. And if you simplify this, then becomes mu, fx is taken as x. This simplifies to the same equation, dx upon dt mu into x. This is a growth characteristic of a exponential phase, and this equation is unable to describe the stationary phase. This is a first order equation and it can be solved at x equals x naught e to the power mu into t. Logistic equations, so it again says dx upon dt equals mu into function of x and this function of x, it takes the logistic equation mu x 1 minus x upon x max. So, if I put x upon x max as beta, so this becomes mu x 1 minus beta x. See, 1 upon x max is beta. This is dx upon dt. So, again it can be integrated, and if you integrate it, you will end up with x equals x naught e to the power mu t divided by 1 minus beta x naught 1 minus e to the power mu t. So, this predicts exponential and stationary phase starting from here to the here. So, logistics means starting from here to here, but does not consider the influence of substrate. There is no way one can see the what will be the effect of substrate on the microbial growth. Now, third equation here is monad equation. It again says dx upon dt equals mu x, and mu we are taking as mu max s upon ks plus s. So, it becomes dx upon dt equals mu max s ks upon s into x. So, this we have already discussed. This is a hyperbolic kinetics, and it applies under limiting substrate condition S. So, these were the three unstructured batch growth model. Malthus law, it explains the exponential phase, simply first order kinetics. Logistic equation, it explains exponential and stationary phase, but it does not consider the effect of substrate, and monad equation, it considered the presence of limiting substrate. Now, we will be quickly discussing the growth of filamentous organism. As we have discussed initially, the growth of microbes can be considered in terms of number per unit volume or mass per unit volume. Now, there are challenge whether n is proportional to m or not. So, in the case of bacteria, we have observed the number is directly proportional to the mass, but when we are considering the molds or filamentous organism, the number is not directly proportional to the mass. Now, when you want to see the how you can model the growth of filamentous organism, the mass and morphology vary for the mold and filamentous organism as growth proceeds. So, once the morphology is changing, then again weight will change. It is not necessary, weight will change only based on the number. Based on the morphology also mass will change. The concentration of mold like cell is expressed in the only in terms of mass per unit volume, not in terms of number per unit volume. And typically these organisms form microbial pellet at high cell density in suspension culture, and cell growth inside this pellet. Once the pellet is formed, they are subject to mass transfer limitations like diffusion resistance. The growth model for mold should include the simultaneous diffusion and consumption of nutrient and toxic byproduct within the pellet at larger pellet size. So, once we are considering the pellet rather than the individual biomass. So, what we say, once you are having the rich medium, the mass and morphology of molds and other filamentous organisms grow. So, once you see this is coming in terms of R size. So, let us say you write dr upon dt as a constant kg, and if you write the mass of filamentous organisms, so it will be density into volume 4 by 3 pi r cube. If I write dm upon dt is equals to rho 4 pi r square dr upon dt, and dr upon dt is kg. So, this becomes kg to 4 pi rho pi r square. This can be further simplified in terms of dm upon dt equals gamma, another constant, m to the power 2 by 3. It is coming gamma as, because gamma we are taking kg 36 rho pi to the power 1 by 3. So, once you are having this expression dm as gamma m to the power 2 by 3, and if you integrate it, will end up with m as m naught to the power 3 plus gamma t upon 3 ka whole cube. So, as we see, maybe initial mass may not be very much significant as compared to the m. So, this equation can be further written as m proportional to t to the power cube. So, for the growth of filamentous organisms, they are slow growing and mass is proportional to the t to the power cube. So, in this way we model the growth of filamentous organisms in the terms of size r, rather in terms of number or the concentration. So, I will stop here for this lecture. So, today we started with this monad equation, how it applies during this steady state condition, and then for the non-steady state condition we need to consider the model for the transient growth. And why it is important? Because any change in the environment leads to the perturbation, and when there is a perturbation, some corrective measures need to be taken place. So, transient growth kinetics is helpful for the process control, it is helpful for the scale up operation. Then we quickly discuss three different unstructured growth model: Malthus equation, logistic equation, and monad equation. So, Malthus equation explains for the exponential phase, logistic equations takes care for exponential and stationary phase, but it is independent of substrate concentration. Monad equation is a hyperbolic equation which considers the limiting substrate and along with the biomass. Then further we discuss the kinetics of filamentous growth. So, here we discuss the change in the mass with respect to change in the size r, and what we end up with, the change in the mass is related to t to the power 3, it is not equals to the t to the power 1. Further, if we just see here in the case of unstructured, let us say batch growth model. So, how to take care of this lag time? Because when we saw this transient growth, let us say diauxic growth, we observed this lag time in the case of both glucose as well as for the maltose. So, if you simply write here dx upon dt equals mu into x, or dx upon x is equal to mu into dt, we can quickly integrate it, but now there will be change in the boundary condition which says x equals to x0 at t equals t lag time. T lag. Earlier we used to write T equals 0. So, once you say T equals to T lag, then if you integrate this, this will be ln x upon x naught equals mu T minus T lag. So, in this way we are able to take care of the lag time, or it will be x equals x naught e to the power mu T minus T lag. So, in this way, in this lag time can also be incorporated when we are seeing this transient growth. So, I will stop here. Thank you so much.